So just like in problem 1, we're going to immediately want to draw a picture of this situation because it'll help us sort of visualize what's going on and let us figure out what direction to go with the solution. So first, we have a bowling ball of mass m moving to the right with a speed v0, and there's going to be a bowling pin of mass m over 3 that is sitting here motionless. Then there's going to be a collision, and after the collision, we're going to have the bowling pin moving up and to the right with an angle of 60 degrees and a speed v0 over 2, and the bowling ball is going to move down with some angle theta and some speed v ball. Now, we're going to define that the right is positive and up is positive. And we're going to use these later on. And note that when we look at this, we can't actually draw this diagram sensibly even though we don't know what theta or v ball are going to be. Because it makes sense that if the bowling pin is moving up, then the bowling ball has to be moving down. And so this intuition is actually rooted in the physics. So looking at this, just like in problem 1, the ball and the pin form an isolated system. And so what that means is that momentum is going to be conserved. And so then we can right away look and see that we can use our familiar equation P initial equals P final. And remember that these are vector quantities, so we're going to have to deal with the directions that they're moving in. So right away we can see that the initial momentum is just going to be m times v0. And we're actually going to split that up into m v0 using the speed instead of the velocity, so it's no longer a vector, times x hat in order to get the direction in there. Now, p final is going to be a little bit more complicated since we have to deal with the fact that these two are now moving at angles. And so what we're going to do is we're going to split them up into components. So the bowling pin, for example, has a magnitude of v0 over 2 and is moving at an angle of 60 degrees. So this y-hat component is going to be v0 root 3 over 4, which is just the magnitude times the sine of 60 degrees. The x-hat component is just going to be v0 over 4, so v0 over 2 times the cosine of 60 degrees. And we're going to do exactly the same thing with the bowling ball, except using the variables v ball and theta. So putting that in as momentums, we're going to get that the final momentum is the momentum of the bowling pin, which is going to be m over 3 times this right here, v0 over 4 times x hat, plus m over 3 times v0 root 3 over 4 y hat. And then all we have to do is add in the momentum of the bowling ball, which is going to be m v ball cosine theta x hat plus minus, this is minus m v ball sine theta y hat. And so now, looking at these, we can set up a system of equations. So we can see that since the initial momentum doesn't have a y hat term, these two y hat terms have to cancel out in order for this equation to hold true. So that gives us our first equation, which is that m v ball sine theta equals this right here, which is m v0 over 4 root 3. And now all we have to do is compare the x hat terms to get our second equation, which is going to be that term right there, m v ball cosine theta, plus this term, m v0 over 12, equals just m v0. And notice that I'm no longer including the unit vectors, I'm now only comparing the magnitudes. So here we can right away notice that we can pull over this term so that we get that m v ball cosine theta equals 11 over 12 times m v0. And so what we're going to do is we're going to square each of these and add them together so that we can use our trig identities to cancel that out, and we get that m squared v ball squared equals m squared v0 squared over 48 plus m squared v0 squared, 121 m squared v naught squared over 144, because we just square that 11 over 12 term. And so adding these together and canceling out the m squared terms, we get that v ball equals the square root of 124 over 144 times v naught, which works out to be just the square root of 31 over 6 times v naught. So now we have the answer for one of our variables, and now we need to find the value for theta. And so all we're going to do for that is we're going to take that equation right there, and we're going to plug in our new value for v ball. So v ball equals square root of 31 over 6 v naught, and we're going to plug that in and pull it over so that we get sine theta equals v naught over v ball. I've canceled out these m terms, times 1 over 4 root 3. And now plugging in this value for v ball and flipping that over because it's in the denominator, we get that sine theta equals 3 over 2 square root 93. And so now all we need to do is take the arc sine. We get that theta equals arc sine of 3 over 2 root 93, which is approximately 8.9 degrees.